Behind the Lines.
All right, good evening, everyone, and welcome back to episode 5 of Behind the Lines, where we bring the experts to you. I'm Francis O'Rourke from GameSense. Hosting with me tonight is Ty Tremblay, also from GameSense.
Hi, everybody.
And this week we'll be talking about mechanism design. As usual, we have a presentation by our 3 distinguished experts, followed by about 30 minutes of Q&A with you, the audience.
So before we hand it off to our experts, we do need to mention, as usual, that the views expressed by Behind the Lines and the guests of those are those of the individual and not necessarily reflect the views of first participants.
That's right. So, speaking of questions, don't forget you can submit your questions to the show by tweeting them with the hashtag FRCBTL, or you can email them to us at btl@frcgamesense.com. Or if you're watching on Twitch TV, you can just type !Q followed by your question, and our chatbot will bring them right to us automatically.
And with that, we're going to kick it off. We're really excited to have 3 great guests with us today. We'll let them introduce ourselves. Alan, go ahead.
Hi, I'm Alan Gregory, mentor for Spectrum 3847. Been doing FIRST for 13 years now. Adam?
Excellent.
My name's Adam Hurd. I'm a mentor on a Team 973 out in California. Been doing this for a long time, and I love everything about it.
Cool.
Good evening,
And last
everybody. Hi, Tyler and Francis. I'm Lucian Junkin. I'm a chief engineer on the Human Exploration Rovers here at NASA, and I'm also the head coach of Team 118, the Robonauts, and also have been leading up the mentoring of the intakes for the last few years, and I love FIRST. Good to be here.
Awesome.
Well, we're really excited to get this show off to the road. So what we're going to be doing is we've chosen 3 typical mechanisms that are used every year, more or less, in FIRST. And that's the collector, the manipulator, which is either an arm or an elevator, and the shooter. And at least one of those has been in almost every single game in all of FIRST history. So to kick it off, we're going to have Lucian start and talk to us about collectors. Go ahead, Lucian.
Thank you, Ty. First of all, the philosophy of Team 118. We can go to the next slide. You know who I am. The philosophy that we have on 118 is if we touch the game piece, then we should own the game piece. Meaning that whenever we make contact with it, we're sucking into our robot. And then the other philosophy that we have is prototype, prototype, prototype. So in the early stages of the year, we prototype quick, and as the year goes on, we take a little bit longer to prototype. And what we talk about is the come check this out moments that we have during the early parts of the year. And then we use this, we break our subsystem into students that go off and do things real quick. I'm going to get ready. I'm going to show you a little bit something that we did. I'm going to use one of the old game pieces from years gone by. I think this is a good example of game pieces of years gone by, or maybe it's not. Maybe it's this year's game piece. So I'm going to take this game piece, and if we go to the next slide, we're going to talk about the old prototype and do it quick. So on the Robonauts, what we do is on day 1, we get prototypes and we do things quick. So we have the game piece and we put a bunch of stuff in front of the students and we say, start prototyping. The drill is a real friendly thing to us. We use these hex shafts, and then let's put a wheel on it. Okay, now we're rolling. Now we can do our first test of the year, and let's do it like this, and sucks it in. But will it suck in this way? I'll be right back. Okay, I'm back. So we use drills. We do small wheels, big wheels, and there's some cool things that this allows you to do. Like this might be good, but it seems like the drill's always kind of popping up. So let's figure out something else to do. So right there, what we would do is after a group of students says, okay, I've got something to show everybody, we show it to them, and then we sit around and we call it 3-minute brainstorming. So we talk about, oh, what could we do that better? Do we have to have some kind of compliance that goes up and down? And then some student will say, why don't we add some wire ties, and we'll take wire ties and we'll throw wire ties on it and see if wire ties, oops, forgot something, safety glasses, because I'm about to poke my eye out. So then you put wire ties and you see if wire ties will, oops, that didn't work. Okay, that didn't work. Y'all go up back. Everybody will go back off and work on their prototypes. And then when I've got something else to show them, then we'll show them. But I got a cool idea right now. I'm gonna take some rubber bands. I'm gonna make one of these rubber band wheels that I've been seeing lately. Take that, take this. Oh, I got it. I think I got, let's add one more rubber band. Hey, Ty, Adam, you guys, this doesn't work. I got that. Let's add some tape to this thing. Maybe. Here's a little wheel. Okay. Hey, Ty. Hey, Adam. Y'all come
What's
on
up?
over, and I got something to show you. Come check this out. Okay, this is, let me get rid of this. Okay, I got this. I got this little wheel thing. Oh, check that out. That's pretty cool, huh?
There you go.
So then,
that's pretty cool.
So that's kind of how what we do is we get the students in a mode of prototyping in minutes, not hours. We give them enough tools, and the tools are all readily available. It's just that we don't use them for prototyping. Like the drills, this is just a hex shaft from Vex, and they're coming out with all these Vex wheels. And I tell you one thing we use a lot of this magic tape. It's basically rubber splicing tape. So then you start doing all of this prototyping, quick prototyping. We have these 3-minute brainstorming sessions where we're like, okay, how about you try this? And then a group of students will go off and try to evolve that prototype. We do that, and then those prototypes take a little bit longer. And if we go to the next slide, I'll kind of show you graphically how we make all this come together. I think this will make all sense right now. So as the weeks go by, we have a lot of come check this out. And then there is, at some point, we like this to be at, I'll zoom back in a little so you can see me. We hope that this is the end of about week 1, where we have our aha moment. Sometimes it's later than earlier. Like this year it was a little bit later. I'll show you something that was a come check this out. Can we play the video of the tote flipping? So you'll all feel my pain right here. So this is a quick prototype, and this is where you get everybody to come over and say, hey, come check this out. This is just like a bar, and this is what I think a lot of teams probably explored. We never really could figure out how to get that flipping mechanism out in front of the robot, but we had some prototypes. We had a lot of come check it out moments, and that's where we ended up at. And then if you go to the next video of the tote gathering, this will be later into that, say, 2-week cycle where I said this earlier, that we strive to get our prototype as close to the flight unit as we can get geometrically with the pressures. This is what we had for this year's robot. We had a student, Danielle was pushing it, and Steven is just ripping the totes out. And so this is our prototype. That's on on just a base we have. It has no motors on it. We use what we call a power drill. We've adapted a regular DeWalt hand and pulled out the motor and just used it as a trigger. And so we just have this prototype, and that prototype is pretty close geometrically with the motors and everything that we used on the flight robot. So that's how we did it. And we can go back to that slide and talk about the graph for a second more. But that aha moment, that's really the fun part of the season for me particularly, is because it seems like when you get to that aha moment, everybody knows that you got there, especially with intake. Okay, that's the direction we're going to go. We've seen a gazillion little prototypes. We get to that aha moment, and then the rest of the prototyping is based around what the aha moment was about. And then I want to take most of my time to talk about the prototyping, because I think prototyping is one of the most important things in FIRST. And if you go to the next slide, please, I'll just go real quickly over the kind of the process that we go. We get finished with our aha moment, and we're ready to get into the design. So a couple of us go off and we start designing in Pro-E. It takes lots and lots of hours, and then we still also have students back prototyping. And that's key. That prototyping is key because all of the students are now engaged. All of them are engaged, and all of them, if somebody's pushing Pro-E and making design work, they can always be over there iterating and improving that. For example, some of that little small wheel in the design, that was an iteration because on the prototype, the tote kept getting stuck in a little dwell. And we put a plate down, it didn't work, so we went to a little small wheel. It's very cool. Then everybody has a design review, and then we go off to the next part. You can go to the next slide, please. And that's where we make parts. And you know what that is? That's machines and lots and lots and lots of hours. And so we're making parts, and guess what we're doing? We're still prototyping, we're still refining. We use that little wooden prototype that we had deep into the season to keep trying to figure out the spring rates that we needed for the intake. What the wheels, that prototype was great for sticking different types of wheels. And as some of you may know, we eventually came up with this rubber from McMaster, like with a 30 durometer, and it was a big hit throughout the year. It was that rubber, water jetted, and the magic I think was cleaning it with acetone after every match, and it didn't rub off the rubber like you do when you use WD-40. When you use acetone and wipe it off, it was as clean as could be, and it really worked well. And then the last but not least is go to the next slide, please. Is maintaining and testing. So we instantly go into testing as soon as the flight unit comes together, and it's the students are, by this time, since they've been prototyping, they're ready to get their hands on the flight unit, and it is test, maintain, test, and maintain. I found this picture over here on the left of Danielle hitting one of the pulleys with a hammer. I don't think I took that picture because may have said something, but it's pretty awesome. So anyway, I really think prototyping is the best part of the year, the most fun, and you can prototype all the way up to championships, all the way up to RI. So okay, that wraps it up for me. Thanks, guys.
Excellent. Thanks, Lucian. All right, next up we've got Adam Hurd from 973 with manipulators.
All right, let's get into it. So next slide, please. Oh, there we go. So first I got to say, got to wear the 330 shirt for talking about arms and elevators. Definitely by accident. Didn't plan ahead on that at all. All right, so arms versus elevators. Most of what I'm talking about here is conceptual and kind of decision making between the different routes you could go, and then I point to a lot of different resources to cover you on the implementation of these different things if you want to do them. So first, choosing between them, part of that is your resources, and part of that is what the game determines. So height required, you have to lift. The room, you have to work on the field. If you can't handle having an arm out there and turning in place, that's going to definitely push away for it. Defense, especially magnifying on that. Whether or not you need to reach over something. I think a really good example of kind of those factors multiplying together and steering different directions is 2007 and 2011. So 2011, I would argue that the elevator was a more dominant design, and there were still some teams with arms that did really well. But 2007, a lot of teams had arms so that they could reach over some amount of defense and make that happen. Some years it's tough to make that decision, but what's kind of in common with both of these is both the arm and the elevator, a lot of these years really are just to get some item to some XY coordinate at some orientation. So you can make a fair amount of wrong decisions and recover from them because you're really just moving something somewhere. I would push towards, unless you have strong reasons otherwise, to always start with a single joint arm. It's hands down the simplest way to get something to about twice robot height, which is historically a pretty common height we're lifting to. To do an elevator and get that height, that's a 2-stage elevator. That's a lot harder. All right, so now let's jump into some of these individual systems. Or actually, motor sizing first. I'm sorry. So I'm gonna do this really, really quick because there's actually a lot of good resources on this already. There's a whole GameSense talk on this already that I was really impressed with and does a great job of talking about all this. But if you don't want to listen to that talk at all and you want to do it off just like one data point, I'd recommend the bag, the mini sim, and the sim for teams that are less experienced, just because they have a much higher thermal mass for the power available, so it should be harder to cook them. And really, if you're just doing this in 5 minutes, then want to move on with the rest of your season, the best way to size is figure out the peak load on your system. So for an elevator, that'll be linear. For an arm, that'll be the arm horizontal. Although you do want to double check, depending on your arm geometry, the arm massed horizontal might not be actually the horizontal location to the weight. So it could be a little off there. But it'll be, the torque there is just that horizontal distance times the load. And then you want to take the motors you're using and multiply the stall torque by about 15 to 20%. 15% more for like the 550 size motors, 20% for some of these motors with bigger thermal mass. And then just size the gear ratio that, the gear ratio times that torque on the motor should be the torque on your system. If that's not fast enough for you, you need to reduce the system weight. You can add motors. Counterbalancing is one thing you can do. However, there's so much power available now that by the time you do the math, counterbalancing doesn't make sense in a lot of the applications. Also, I would resist the urge to make stuff really fast because you see 284 has it really fast. There's a lot of reasons making it faster makes things more difficult for you. And often, most teams just don't hit a level of play where that speed is useful. They're still driving to the other end of the field, and they have plenty of time for the arm to finish the motion. All right, so next slide, please. So single joint arms, 330 definitely is king. Find a way to make those work in more years than I would have guessed. I did 2 rant videos that are solidly mediocre on single joint arms. Talk a lot about the implementation. Really what I'm going to go for most of the things today is just make everything out of VexPro. Like if you're at the point where you don't know how to implement this stuff, VexPro has a good solution for like 90% of this. And the last 10% you guys can solve on your own pretty nicely. VexPro has an example of a single joint arm linked at the bottom here. I would try to copy what 330 did in an ideal world, where if you zoom in on this picture on the right, they actually have an intermediate sprocket before they go to the final thing, so that if you were doing like a versatile here, that would hide the versatile behind 2 stages of reduction, make it a little more robust. All right, let's jump to double jointed arms. All right, double jointed arms, I think, kind of fall into 2 categories, and one you don't see that often is when you really have like 2 full arm joints, like 2 4 or 5 foot sections. Haven't really had a reason to do that in a long time. Most of the time you see them, that second joint is really just a wrist, and really the decision you're making between the 2 design styles there is, as you move the primary joint, do you absolutely need the second joint, the wrist, to maintain its angle mechanically, or are you okay solving that in software? To change that angle as you go up, or just live with the angle changing as you go up. If that's the case, it's really, really easy to do a 2-jointed arm using VexPro stuff now, if you don't want that virtual 4-bar. And I've linked our 2011 CAD in here if you want to see how we did that kind of fancy. But actually, if you're a little clever, you can make the full virtual 4-bar like we did in 2011, completely out of VexPro stuff without much machining at all. So I'd really push towards that. All right. Let's jump ahead to elevators.
Before we just to really quickly say, for those of you watching right now live, you can't click on the link because it's Twitch TV, but this will be up on First website for you to download and click the links all you want as well later on. So go ahead, Adam.
Alrighty, let's jump ahead to elevators here. Elevators are really cool. I'm kind of a much bigger fan of elevators now than arms, but they're a good deal harder to implement than a single joint arm for a lot of teams. The good news is just recently now, there's some good COT solutions to the bearing setup. There weren't really great solutions there before, so you had to really do that all custom. Really the fantasy, and this worked out in 2015, but not a lot of other years, is a single stage elevator is more than twice as easy as a 2-stage elevator, hands down. And that's why going back to that single joint arm, if you want to lift 2 times robot height, the single joint arm is hands down far easier than a 2-stage elevator. But if you do want to do 2-stage elevator, I'm really kind of copping out and linking to all these other resources. It's way easier to link to existing stuff than doing it live. But I did 4 videos on elevators, and I talk about a lot of different things in there. So if you're interested in elevators, I would definitely look at that. And once again, I'm going to reiterate, if you don't know what you're doing here, the best thing to do is make the elevator completely out of off-the-shelf stuff, and VexPro's got most of that for you. All right, let's move on to mechanical tips. All right, some things to keep in mind on a lot of these is tensioning. If you have any sort of chain in your power transmission, you need a plan to tension that, or be aware of the cases where you don't need to tension that. I really, really love the versaplanetaries, but for a big arm or something, you can't have that as the final output, obviously. So you want to hide that behind 1 or 2 stages of further reduction, and that could be like chain and spur, and then the versaplanetary, or that could be like 2 stages of chain. And I don't know exactly why, but I've heard that the 5, 7, and 9-to-1 are the stronger output stages for the versaplanetary. So for whatever ratios you're doing, try to end up with those as the output. Hard stops are a big thing. A lot of people miss initially. It's kind of nice to think that you'll never crash your system, but you will at some point. So you might as well decide where it's going to hit and what it's going to hit. For us personally, I then like using the hard stop as a 0. So all of our arms and elevators the last 4 or 5 seasons have all had incremental sensors, and we zero those just by crashing into the hard stop, and then you're on the hard stop, and you can zero from there. Sensor placement is absolutely critical. You see a lot of teams just skip it and then try to tack it on at the end, and then that makes things a lot more difficult. So do the electrical and software team a favor and design those sensors in from the get-go. When you do that, make sure the sensor resolution you're designing in makes sense. Don't put a 5-turn pot that you're only using a half turn on and waste all that resolution. That'll make it a lot harder to control. This next point, I think, is really big. You run into a lot of teams at regionals that have trouble here, and that's don't gear super, super fast because you see 284 gearing super fast. It takes a lot of design insight when you're designing it, and then good software to control something that fast. And it actually gets exponentially easier to control stuff that's way slower. You can kind of view it as like an energy storage thing. When your system's going slower, there's just less energy going into and out of it, and your motor's geared down way more. So you have more torque available to put energy in and out, and you can really slow that down a lot faster. And then also, if you do a lot of reduction, that's just a lot of friction, which acts as a nice free damper. One trap I see some people fall into too while we're on control is preset positions are really nice, and I recommend you use those, but you'll sometimes see people implement that and then have no backup whatsoever for manual control. So whether that's your sensor fails or the practice field was different than the real field, you want some methodology for your drivers mid-match to deviate from your presets, because it's just painful to watch a team go out there like in 2011 and have the arm 2 inches off and every tube they're missing, and they got no ability to fix that mid-match. So make sure you leave yourself room to do that.
Yeah, Adam, to piggyback on that, on your note about going slower, one of my favorite phrases for first is slow is smooth and smooth is fast. And I think that can apply for the way you drive, the way you control your elevators, and the way you control your arms for sure.
And one point I actually missed there, and thank you for reminding me of that, is like by definition, if you gear too slow, it's very, very easy, especially if you're using Versaplanetaries or Vexpur gears or chain, to gear faster. You can always make your driving sprocket bigger and that sort of thing. However, if you don't gear down enough, you're often adding substantial stuff to your robot to change, and you may be bottlenecked into a corner where you can't make the system slower without substantial rework.
Agreed 100%. All right, go on, continue.
That's all I got.
All right, thanks a bunch, Adam. Next, we'll just jump right into it, and we're going to move right on to shooters, prototyping and design with Alan Gregory from Spectrum.
Awesome. Thank you, Ty. So Lucian talked a bunch about the roller collectors. A lot of the prototyping that we do is very similar for shooters. You're going to be using the same type of materials a lot of times to do the quick prototypes, just going to see how things interact. But you're trying to identify what the variables are going to be for the individual shooter for that game. You're always going to have to figure out how fast you have to shoot the object, your launch angle, both vertical, and what direction you're going to have to shoot it, whether you need to shoot sideways from your robot or you need to have a turret, stuff like that, and how much spin you're going to put on the object as well. Most of the time, for the large majority of the teams, if you can fix as many of those as possible to where you can't adjust them mid-match, you're going to be a much more reliable shooter. So if you have a single launch angle, you don't have a turret, it shoots with a single spin, a single velocity, and you just shoot from a single spot on the field, you're going to make a much more reliable shooter than if you were to have a very variable shooter that you have to control everything. You have to have a lot of control systems running. There's not a lot of teams in first who can do that and do that really well. Prototyping allows you to figure out what those settings are, and that's what you're trying to figure out in this first few weeks of build season is what are all those different options. There's a ton presented to you at the beginning of the season. You know you have to get an object into a goal, but you just have to figure out how. So prototyping is something that can help you do that. Let's move on to the next slide. So there are, most of the time, and I'm going to pretty much exclusively talk about wheeled shooters, because there are times where you want to build a catapult, but most of the time in most games, there's a way to do it with a wheeled shooter. Most of the motors in first, or we have a ton of motor power in first, so it's very easy to spin something quickly and with a lot of torque. So wheeled shooters are very often the solution, just like roller claws are very easily the solution to pickups. You can do a pneumatic clamp or something like that to do a pickup, but most of the time you're going to be faster and it's going to be easier on your driver if you have a wheeled shooter or a wheeled roller collector, same type of thing. One of the things we do is we have a giant bin of wheels. It's actually sitting next to me. So we have all sorts of wheels that we can easily throw hubs on, and we can test and figure out what actually interacts with the game piece. There's so many different wheels we have now from COT Solutions, from Andy Mart, from Vex, from McMaster. So just getting some of them, even if you only get one or two, and having them in stock, so you just know, okay, so week one, day one, whatever, you can build a shooter really fast and just figure out, does the pneumatic tire work better? Does a roller work better? Does a Banebot's wheel work better? You can kind of figure that out and know really quickly. Have different diameters, different widths, different weights. All of those are going to impact whatever it is depending on the game object. You'll have a very different shooter if you're shooting a Frisbee compared to if you're shooting a basketball from 2012. You also want to be thinking about how they wear. So a lot of times, once we figure out a prototype kind of works pretty well, we'll run a lot of shots through it and see if it can stay consistent, see if the wheels are wearing down. That was a big problem with Banebot wheels in 2013 when a lot of people used them as Frisbee shooters. They wore down a lot. Some of the McMaster urethane wheels didn't have that problem, and they were running 9-10 competitions without ever changing. Cost will also be a factor for teams, but that also goes into wear. If you're only playing one time, you might be okay with a cheap wheel that will only last you a little while, but if you're going to be playing a long time, you're probably going to want to buy a better wheel if you can afford it. If you can figure out a way to make the hubs, those can be complicated too. I have some resources that I've made in the past to show how to make cheap hubs for some of those types of wheels that don't come with them. That'll make them a little bit easier for you to use. For pneumatic wheels, especially when we're talking about shooters, you want to make sure that you can figure out a way to dial in the pressure, have pressure gauges, have people who are maintaining and checking that. That was a big problem for a lot of pneumatic wheel shooters in 2013. They'd be off one match because their pressure was a little low. And then anything that actually touches the game object as it's leaving is going to affect the shot. So your opposite wall, oftentimes, if you have a one-wheeled shooter that you have a Lexan or some other wall, if you change that traction material, you can also change spin. You can change a lot of different things about the shooter. Okay, next slide. Okay. All right. A couple of the pictures I had didn't get put up here, but so this is actually a photo from the 2013 season. This was a really quick prototype that we did, I think, in the middle of the second week of build season. And we had basically 2 versaplanetary gearboxes, just like Adam was talking about. They're really quick and easy to use. We threw a couple of Banebot wheels on there, and we were shooting frisbees within a matter of hours. So as quick as we could, we had a drill, just like Lucian was talking about, that we were able to power them off of, and you can change the speed on them, things like that, where you can get a very, very quick prototype done, and you don't have to worry about building something complicated, anything too big. Just this past week, getting ready for build season, we had students in here working on prototypes, kind of like what Lucian was doing, and we actually were shooting a rugby ball, trying to figure out how to do that. We had a versaplanetary hooked up to it. We had a drill modified to just give it a voltage, and we were getting very, very quick tests done through. We could change compression. We could do all that just by moving wood screws around, things like that. Another one of the main prototypes that I think everyone has seen, Adam has built a whole robot based around it, was the Cheesy Goose prototype robot from 2014. That was a whole robot built that way, so they managed to integrate all of their systems all the way up to making sure that their shooter worked, because they wanted that level of detail before they had a final product. And you can get a lot of that same type of testing done with your prototypes. Okay, next slide. Okay, so shooting in first, the number one thing, like I already said earlier, is you need to be consistent. Well, there's a lot of teams who can throw an object hard, especially like Big 2014, where you had robots that were just launching the ball all the way across the field. But if you couldn't make it in the goal, it wasn't really helpful, and it hurt your alliance more often than not because you were missing. So if you can find a spot on the field that you can shoot into, and you can hit that spot every single time, you're going to be much better off. And it also requires your robot to be consistent as well. So you need to have a rigid assembly, so you don't need to have it moving around. It's very easy to look at a shooter and go, oh, if that takes a hit, it's going to, the wheel's going to move or things like that if it's not constructed well. You also want to make sure you have a very consistent loading solution. This is one of the things I think 118 did extremely well in their 2012 robot that helped them get all the way to Einstein, was that every time that ball went into their shooter, it happened the exact same way. So every single shot was hitting the wheel the exact same way every single time perfectly. Consistent speed, this goes into programming a lot of the times, but it doesn't have to be complicated on programming. Hot's 2013 robot, their frisbee shooter, was one of the most accurate full court shooters, and it was just full open loop, 3 motors at full speed, and the driver just timed feeding the frisbee in every single time, and they got a very nice shot doing it that way. So if you can get consistent without doing programming or without doing full PID, if you can do something like a bang bang controller or anything you can do to just make it a consistent speed, you get a consistent shot, and it doesn't have to be a ton of work on your team if you don't have a bunch of programmers, you don't have people who can do that, figure out a way to do it without that. And then also, just like Lucian was saying, you have to be able to maintain and you have to be able to take care of the wear that happens on the shooter. We're spinning these wheels extremely fast, most of the time way over what they're rated for or anything like that. We're running them into objects. They're going to wear down a little bit, and we want to make sure that we either are replacing them or we're cleaning them or maintaining them so that every time we put it on the field, we're going to be able to get a consistent shot out of it. We're going to be able to get a consistent result from what we know we can do in prototyping and in testing throughout the season. The other thing that we always have to deal with, and it's pretty much part of every game, is the game piece. It's not always going to be consistent. In 2013, it was pretty consistent, so most teams were able to get very good shooters. In 2012, we had a huge discrepancies in the balls to the point where you knew you didn't have a consistent game piece, so teams turned to actually making their robot adjust to it, all the way from having scales on the robot that could weigh their autonomous balls before matches, to having different force sensors or scales on the robot so they could figure out how squishy the balls were and things like that, and they could actually adjust the compression or speed of their shooter to actually get a better shot coming out and getting a consistent shot. Another thing you should plan to do is iterate on the actual final robot. So just like Adam said, you should build in sensors, you should also build, especially in your shooter, ways that you can dial it in. So you want to be able to change that compression ratio. You want to be able to change your speed, so hopefully you'll have a way to adjust velocity a little bit. Give yourself a range, change angles, change hard stops, things like that. So you can, if the game pieces you get to and they're a bit squishier than the ones you had at your home, you can dial in your robot a little bit and make sure you're getting a nice, consistent, clean shot every time. You also want to be able to analyze your results both on your prototype and on your real robot. A lot of teams have turned to high-speed video for this. It's gotten way cheaper to get over 120 frames per second. Most GoPros will do 240. You can get point-and-click cameras now that can do, I think, 10,000 frames per second or something ridiculous. So you can slow that down. You can see frame by frame exactly how the game object is interacting with the wheels, with the sidewall, how much spin it's getting, the exact velocity. If you can put a pattern background behind it, you can see exactly how far it's moving per frame. So you can get a lot of interesting information coming back from your shooter that you can then use to tweak and dial it in again as you're iterating throughout the season. I think that's all I have.
All right. So we will be uploading, like Francis said, we'll be uploading this presentation, so you guys will have full access to all of the links in the presentation that we referenced, as well as all of the videos. So we are finished with the presentation side. We're going to move on to question and answers, and we do have a lot of questions coming up, so this should be a pretty great discussion.
Yep, absolutely right. So if you haven't asked your question yet and you want to ask it, you can either tweet it with the hashtag FRCBTL, or you can email it to us by emailing btl@frcgamesense.com. Or if you're watching on Twitch TV, type !Q and then your question, and it will automatically get sent to us via our chatbot.
All right. When we are waiting for our chatbot to toss us up our first question, and while we do that, I will pose it. Let's hope that this is the first question that gets picked. With wheeled intakes and shooters, how do you pick speed and or gearing, since it's not a well-defined force? So let's toss this over to Lucian first. Lucian, how do you choose how fast to spin your collector when you're in the prototyping stage? Oh, you're muted.
Sorry about that, Ty.
There we go.
No problem.
Yeah, give you an example of this year's robot. So we have the prototype. We start with the drills, and we find out how quick we want the tote to come in. So we're worried and focused on speed, speed, speed. Let's try to fine tune the speed, and then we'll start selecting the motor. When we look at the motors, we use 75% of no load speed as a starting point of how fast those motors are going to run under normal loads. And this year we were in the mode of we want to constantly slip the wheel this year on the totes. And that, just like you put your viewer pointed out, it is a non-trivial problem of we have this force coming in, that we have a spring rate pushing our wheels in, and then how much force are you getting and how much so. In this case, we took more power than we needed, and this goes back to Adam's point, is throw more power at it, and then you can always back off. But you can't, if you throw too little power at it from a motor standpoint, then it's hard to up the speed when you want to get it in your robot. And we were trying to optimize it between the base of the robot going through. You saw Danielle eating up totes. It was an integration of how fast do we think the lift is, how fast we think we can go into the totes, and then so how quick do we have to get them. So speed, speed, speed first. Try to put more power in the motor from a selection standpoint. Use 75% no load speed to kind of start down that journey, and then you're able to gear it from there if you need to tweak it.
Yeah.
Cool. Back to you, Ty.
One of the rules of thumbs that I like to use for roller collectors is the surface speed of your roller collector, that's in how fast the surface of your wheel is going when it touches the game object, should be faster than your robot is moving when you collect the game object. If it's slower than your robot's moving, then the relative speed is actually you're not going to be able to collect your object at all. So, for example, in 2014, we had robots that could go 15 feet per second or even faster, So you wanted to have, and it was a very fast-paced open field game. So you wanted to have your collector going at least that fast when you were running it. And conversely, so to speak, in 2015, since it was kind of a packed field and you had to maneuver more accurately, you could get away with higher torque and slightly lower speeds because your robots weren't going 15 feet per second while collecting.
Yeah, that's a good point.
Oh, and can I jump in for just 1 second?
Certainly.
There's another thing that we've used for years that I'd like to share with you is we use pulleys, and we use pulleys with eagle belting, and what we do is put our motor on the pulley, and we have one pulley, and we use this as our clutching. So if you just take a pulley and you use eagle tubing, and you can use that as your clutch. Now, this ladder, there's a lot, the current sensing on the motor controllers has become really good, so you can all use that. But those balls in 2012, they really were sticky, and they would clog up your intake, or clogged up our intake often. And we could always just slip a belt, and then when it was ready to get in the robot, then it would just suck right in without burning up a lot of motors. And oh, by the way, when you prototype with real motors, go out to AutoZone and get you a little fuse and burn up fuses instead of burning up motors. That's another trick we use to save hundreds of motors around here.
And hundreds of dollars.
Yes.
And hundreds of dollars.
Well, that's awesome. All right, we're going to get ready for our next question here. This one, we're going to throw it toward Adam first. Adam, here's your next question. What are some considerations for being able to control an armor elevator at faster speeds?
Whew, okay.
We only give you the easy ones here, yeah.
So, I mean, for starters, at low speed, backlash, and huge lack of stiffness. That sounds badly. Whatever one word for huge lack of stiffness is, will present a lot of problems at high speed. Because at low speed, you'll do the motion and end up, and you might have a little wiggle that you don't really notice. At high speed, the backlash and lack of stiffness will cause a lot of excitation. On the control side, it's kind of hard to say rule of thumb, but most teams are running, their control loops right in the main robot code, which is triggered by the receipt of the packet. So it's not in constant time, and it's happening like 50 hertz or something. For some of the real fast systems, you might need to split into a separate thread. I don't know if teams are doing actual constant time or just closer to constant time because it's in their own thread. But I know teams are going at like 200 hertz now. You want to minimize the amount of mass in your system, just because that's inertia saved up. So, like 469 was super, super fast in 2011, but when you actually look at their elevator's moving component, there wasn't much mass to it. A lot of other teams with full roller claws could not have come even close to that speed, just because stopping that would not have been very easy. Because you also have to keep in mind, if you want an elevator to go 8 feet in 0.6 seconds, if you're running at 50 hertz, your robot only sees 30 data points on the way to the top. And actually, I think 469 actually crashed into the top to stop. I'm not sure they actually stopped with code. So yeah, that's a couple things to look at, but there's a lot more to it once you get past that.
Yeah, one thing to consider there is the Talon SRX is actually kind of its own computer in a way to speak, and it's a good way to distribute the amount of processing that your robot has to do on the field with its main CPU. The Talon SRXs can actually run their own control loops, and they run them at crazy fast rates.
Yeah, they're doing 1,000 hertz. That's real good. And that reminds me of one of the biggest software things you run into when trying to go faster is when you get to those speeds, you need some dampening from your control loop. You need the D and PID. And now you need to do much better logic when you pick your sensor so that the velocity term coming out of your sensor isn't really noisy. So, I mean, if you pick just an average quality pot and don't filter the output either electrically or in code, and it's has a little backlash, yada yada, the velocity signal coming out of that will be all over the place, and your D term and your control loop's going to be reacting more to that noise on velocity than the actual system, and you'll hit a speed bottleneck just on that you can't overcome.
Cool.
Another safety feature for the Talon SRX is you can plug in forward and reverse maximum travel limit switches,
Yeah.
and those will, on the motor controller, immediately disable the motor travel in that direction. So if something does go crazy and the motor continues past, it'll stop and prevent you from eating itself.
Both of the new speed controllers do that as well.
Yes, correct.
Yes, all those now hundreds of speed controllers we seem to have to use these days.
All right, moving on to our next question. How does inertia affect shooters? So this one will be for you, Alan. How do you deal with a sudden speed drop when a game piece engages with a wheel? And this is from Munch Skull.
All right, so the inertia affects your shooter mostly in spin-up time and your time to your next shot. So if in a game where, like in 2012, where you need to shoot 3 balls in rapid succession, you wanted to make sure you had enough rotating mass that you could maintain speed while the balls were going through your shooter. The initial sudden drop is going to be part of your prototyping and figuring out how much torque you have on your motor to be able to maintain speed and how much inertia you already have on your wheels spun up that you can maintain speed as well.
All right, how do you maintain as much speed as possible? What were some of your recommendations for that?
Similar to what we've already been saying, if you can throw more motor power at it, it's going to be able to have more torque and it's going to be able to stay at speed even as you put a load on it. So if you're not gearing it, if you're gearing it to more torque as well. But to do that, you normally just need to add motor power because you're going to be on your shooters, you're spinning somewhere in the neighborhood of 3,000 to 15,000 RPM depending on the game. So you're not going to be getting that much torque out of any single motor. So that's when a lot of teams start adding multiple motors to their shooter wheels and things like that to be able to get up to speed faster and maintain that speed.
Yeah, that's a good point. And sort of one of the tricks that you could try to do as well, if you can overpower, like put too much, like not too much power, right? But you can put more power into your wheels than you need. If you can run your desired output speed at less than full motor current, then you can basically, after it shoots through, you can have your PID or control loop if you're using that, boost the current up to full. You know, if you're going really dumb like me, set it to you can't go any. You know, your maximum your shooting speed is like 100 PWM, and you can go up to 127 after you're done shooting. So you come right back up to speed quickly afterward.
Yeah, a key part about what he's saying there is if you look at the motor curve, as you hit free speed, the torque drops off, so your acceleration really junks out. So I think a lot of teams in 2012 picked their operating point to actually be at like half the free speed of the motor, and then that's a distinct advantage to teams able to run a control loop because you can give it full gas, you know, almost all the way up to that operating point and really accelerate a lot quicker than, you know, if you're just giving it a 0.7 output or something like that.
Yeah.
And a mechanical solution that you can add is to actually make your shooter wheel very heavy. And that was actually something that 254 did in 2014, is they actually added a lot of weight to their wheel because they had this huge, like 24-inch ball that had a lot of mass to it. And I don't care what motors you're putting on, it's going to slow that wheel down significantly when you take your shot. So they actually put a lot of mass on that because it would slow it down so much that it would affect shooting just one ball. As soon as the ball touched it, the velocity of the wheel would slow down significantly between the ball touching it and the ball exiting the shooter.
Right, and as you add mass, you're going to increase your spin-up time, though. So they were able to use that first 5 seconds of auto to spin up their shooter to the right speed, and then because it was heavy, they were able to drop those 3 balls out very quickly.
Exactly. Right. Yep. And of course, you know, we have this weight limit thing too, which can be a bit of an issue sometimes. But yeah, if you guys look up on YouTube, go to search for 190 2012 shooter explode. You'll see what a heavy shooter wheel can sometimes do. But we're going to move on to our next question here. This question came in from Twitter. Question is asked: Can you guys talk about the precision with any of these mechanisms? Are sensors essential? Manual stops only. Driver practice. And this is asked by Christine. I'm going to throw it to you first, Lucian. What are your thoughts on this? What do you guys find works the best? Is it a combination? Is it one or the other? Or
our philosophy is design with sensors, and then back away, do enough testing to find out that you don't need sensors. For instance, on our arms this year, our intake arms, we had sensors to tell us how wide they were, and we designed them in But then we had pots. I think they were single turn pots, and then we found, oh, we don't need them. So then we abandoned that. It's easier to abandon than not to do it. We use string pots. We are, we're huge on we are big on trying to know where everything is, and we probably overdo it, but we are very good at backing off after we find out that the flight units come together. And from a strategy standpoint, we really don't need them. We use hard stops. I love hard stops. Hard stops with limit switches that will turn motors off. But this year we had good current sensing, so we didn't need as many limit switches.
Before I ask Alan to sort of give his take on that, I want to just say that Lucian, a member of Team 118, has admitted that sometimes 118 overdoes it. We've admitted it now.
Sometimes.
It's on tape.
I admit we
Once in a
always
while.
do it.
I think you're allowed to overdo it when you anodize or when you coat your entire robot in gold.
All right, Alan, what are your thoughts on this? You guys don't necessarily have all the resources that 973 and 118 do. So what do you guys do?
So it depends on your things. For intakes, a lot of times for positioning, we like to use pneumatics. So for our 2014 intake, if you can set it to one or two spots, something actually I'm missing the shooter presentation. If you need to angle your shooter, but you only need to have it as two choices, a pneumatic way to do that is going to be better. You're going to have two hard stops. You know exactly where it is. You don't have to worry about motor control, PID, anything like that. As far as sensors go, especially on shooters, you're normally going to want some way to get an encoder to know your speed. But it doesn't have to be it doesn't have to be a fancy Gray Hill encoder or anything like that. A single light sensor with a wheel painted white and black will get you more than enough resolution when your wheel's spinning at 3,000 RPM to get you where you need to be for a bang-bang controller or something simple like that. It doesn't take much line of code to program at all. Pretty much anybody can do a bang-bang controller. You look it up on Chief Delphi. It's literally on and off. That's all it is. And it works well enough for a lot of teams in 2012 and 2013 as well.
Cool.
I think a key general point here, too, is across the board, the relative precision required for any of these arms, elevators, or shooters will go down the more you prototype and the more you play with it. We didn't prototype our shooter that much in 2012, so for us to make shots decently, we were measuring ball firmness, we had to hold RPM almost perfect, and we had to control the conveyor velocity on a ramp down as it fed into the flywheel. And then there were some teams with much better optimized shooters that could just feed the ball in totally open loop with the conveyor, and the ball would go in every time. So the more time you can solve, or the more time you can spend solving problems prototyping, the less precision you'll need on that final product.
Yeah, the rule of thumb that we use on 319 is an hour of prototyping will save you at least 2 hours worth of debugging and tuning.
Oh, if not more, yeah.
Mm-hmm.
Yeah, and one other comment on sensors is teams should explore. If you don't use the gyro yet, explore using the gyro. Start to understand it. It's good for first robots. IMUs are good for robotics in general as you grow up. So don't necessarily jump in and say we're going to use it, but if you have it, it makes Auton nice and such. And we learned that lesson from a lot of other really good teams.
Talking about the IMU, the NavX has come out in the last couple of years, has helped a lot of teams do that really easily and simply, getting precise angle throughout the match.
Mm-hmm. All right, on our next question is directed to Lucian. Why do 118's robot always have so much stuff on them? How do you manage integrating all of these systems?
Okay. They don't have that much stuff on them.
Says the NASA engineer.
So let me explain to you our process, and then this may make it clear. On Sunday after kickoff, on the kickoff day, we try to understand all the details of the game and the rules. On the Sunday, we don't try. We put together our robot wheel list. And in anticipation of this thing, I brought you a robot wheel. I mean, these stay around forever. This is our robot wheel list from Endeavor from 2012. And it's got the list of things that our robot will. We keep these forever. We put them on pieces of wood. they're forever. They're forever there. So if we look at shooting, we're gonna shoot high. We're not gonna worry about shooting in the low goals, and that's kind of how it was. And so if you come out Sunday night with all of this ambition, then you start to have a lot of subsystems, and you start to try to do it everything. Okay, ladies and gentlemen, yes, we are a little overzealous in trying to do everything every year. We tell ourselves this, you tell us this, and we try to scale back. But doing that Sunday allows us to have effectively an extra week to build a robot and to anodize a robot. And oh, by the way, we do anodize all our robots, all our real job robots, the same color. It's a partnership we have with our coding company. So, but then that comes to the point of how do we integrate all of that? We integrate that. We do design reviews. We do what we call, and I would say this happens at about week 2.5. So let's go back to what I was talking about earlier. We have our aha moments and kind of how things should come together at about week 1.5, and we start to understand those things. So we're pushing CAD by the end of week 2. And we call it, what we say is we have crayon CAD. So all of the students and everybody, we start to, for years we drew the base on the floor, and we would cut foam and stuff and start positioning all of the components all around the robot. And we get down to the battery, and we try to integrate like that really, really early on to see what the interferences are. As the years have gone by, we use Pro-E a little bit more for that, but we still do physical representations of the robot and kind of piece everything together to do the integration. So the way we do it, the way I think that we do a good job integrating, is we start early and we're always integrating all the way to the end. And with that said, yes, we made some monumental problems over the years.
Well, you know, I always love seeing your videos because there's just so much going on and there's so much fun. And you know what? You built some really good robots out there, so I can't really complain. Can't say it doesn't work.
And we intentionally carry 60 students on the team, and when you have that labor force, you really can knock out a lot of work. And I know a lot of people walk into our pits and say, hey, that must be NASA engineers. Of course, NASA engineers built that robot. And that really couldn't be not further from the truth. If I gave the same challenge to 60 NASA engineers around here, we couldn't even come close to building the robots we build, much less building them in 6 weeks.
Yep.
So having all those students really does help out a lot.
Yeah,
Cool.
And I'll tell you, man, in 2013, when we watched that reveal video, and then at the end, all of a sudden it decided to climb the pyramid all the way to the 3rd level using a wheel as well. That was like one of the most amazed experiences I've ever had in FIRST.
Thank you.
Cool. Alrighty, we're gonna go on to another question here. I'm gonna shoot this one to Alan first. Question is, I'm from a team that is pretty inexperienced. If we don't use a sim or mini sim, what would be the best motor gearbox combination to use for intakes wheels? Now I know this is going to change depending on what you're picking up, but Alan, what are your thoughts on that?
So for intakes, we've been mentioning it all episode. We're big fans of the Versaplanetary gearbox from Vex Pro. It allows you to use a ton of different motor options. Either the bag motor or Andy Mark's 9015 motors can all be put into there. You can put a sim or a mini sim in there if you end up needing to have more power. And they allow different output options and things like that. There's also a few ways that you can make other motors into sims. Andy Marks and Vexpo sell different options for that as well. So if you have a tough box sitting around and you want to use that as your intake motor or gearbox for some reason, you can do that as well with a different motor, and you can make them all kind of get that same 8mm output that the sim has.
Cool. Adam, what are your thoughts? I know you were talking about this in your part of the presentation. I have a feeling I know what you're going to say, but...
Definitely the Versaplanetaries.
All right, there you go.
There you go. Short, sweet, simple, and to the point.
Yep.
Just use a Versaplanetary.
Yep.
There's even this summer people posted ways to integrate an encoder right into them, so they're getting even better.
Wait, what did
Cool.
you just say?
They have this summer there's a how-to on how to like integrate an encoder into them. We did a version that we posted on the blog, but it was done off a version of a team I can't think of off the top of my head right now. But they drill and integrate an encoder right in there, so you get feedback directly from it.
I believe that was
okay.
2363, just for reference.
That sounds right.
All right. Our next question is directed to Lucian, but it is about shooters. How did 118 come to or think to use the foam shooter wheel in 2013? Can you talk specifically about what material that was? And that is from our font just wrecks that name, so I'm not even going to try to read it.
Mamarandola 3.
2013, 2012 was Endeavor. What was the? Oh, I'm about to get my age. What did we do in 2013?
Frisbee shooters.
Frisbees.
Oh, frisbee shooters. Yeah. So we were struggling. It was, those come check this out moments. So we had a shooter, and it was a plywood prototype, and we had 2 wheels, and it was the end of the night. We got the whole team together, and we said, come check this out. I remember the night we pointed that thing to the goal, and the Frisbee literally went 1 foot out of the shooter. 1 foot. And those wheels were howling. We had 2 wheels on the side. And then from that prototype, we just started pounding out every different type of material that we could possibly find. And we had some, I think it might be space rated packing foam around here that we cut up. And all we did was put it on put a template on a bandsaw and put a hole through it and just spun it on the bandsaw. It took us like 10 seconds to cut one of those things out, and then squeezed them with some metal and put them in there. So that was nothing but walk around campus here at NASA, try to find materials and stick them on there. And we knew we would come up with some material at some point. Because I think that, and you got to remember in that prototyping, we don't know that everybody else can even shoot this Frisbee. Oh, we're speculating that there's no one that can figure out how to shoot this Frisbee a long distance because of our massive failure from that one prototype. So that's kind of how we came up with it.
That's pretty cool, actually. Can I, real quick, Adam and Alan, what are your guys' favorite sort of shooter wheel materials? Do you guys ever make your own wheels or use your own coating or anything?
So just to chime in on the packing material real fast, I know from personal experience that the packing foam they used is a great pillow on the way to St. Louis. We had some. We took some leftovers out of their lab. It worked very well. In terms of shooter wheels, there's so many COT solutions now that we have Colson wheels or urethane wheels. The ones that a lot of teams have been moving to are ones like this. You get the McMaster car urethane wheels. They're the same ones that 2056 I think started using them in 2012, and 1114 used them in 2013 as well. You have to make a hub, but I have a blog post on how you can use 1/2-inch hex shaft collars to make a pretty decent one. My first try, it actually spun pretty true. I was really surprised. I thought it was going to vibrate like crazy because you just press in shaft collars and you actually get a pretty decent wheel out of it.
I think the first question you got to ask yourself when you're looking at shooter wheels is, some years the grip really, really matters in the interaction, and other years it doesn't matter as much. So like 2014, the ball was relatively grippy, so I think the material on your wheel, if you were doing a shooter, wasn't as critical. But 2013, it definitely mattered a fair amount, and that really steers what direction you go with to start. I would advise 99.9% of teams to try to find a COT solution to your shooter wheels. There's so many available now, especially now that the community has kind of felt out and found some of these trick wheels like the blue ones that Alan was just showing. And then that same company, Fairlane, makes a white one that's got like teardrops cut into it. That's been pretty popular too. That one's on McMaster as well.
There you go. There it is.
It seemed like in 2012 that if you took the 8-inch Andy Mark wheels and turned off just enough to like break the skin on that rubber, that those are pretty good. The like Andy Mark kit apart wheels. So I would put a lot of effort into trying a bunch of different wheels you can get versus trying to do a bunch of science and figure out what you can put on something.
Mhm.
And I couldn't agree more with Adam. If you think we're the right way of doing it, that's you're wrong. And we do turn it into like we did turn it into a cot solution with that foam. It was the students were cutting the foam. We'd cut the foam on the bandsaw. They would put a hub on it, and we would try the next thing. But Adam's right. There's so many good solutions out there. The real thing is how you find that cot solution quickly. So I hate to keep harping on prototyping. When you build your prototype, you need to think, I'm not building it just for this wheel. I'm building it for the 20 wheels that I'm going to try and shove through there and make like the Frisbee. We had on our prototype, we had that wall that it was interacting on the other side of the wheel, very adjustable. So we could tune it to, 1/16 of an inch.
Yeah, and also try wheels that you don't think will work. So we actually got to our collector in 14 because we just threw a mechanism wheel on there and said, hey, maybe it'll work. And it worked fantastically. A ton of teams ended up coming onto the same solution or using it as well throughout the season. But most of us, when we thought, we had no idea it would work. We also, at one point in 2013, tried to shoot a Frisbee with an Omni wheel. That did not work at all. So,
Ooh. Well, hey, you live and you learn, though, man. All right, well, guys, thank you all so much for joining us tonight. This was an awesome episode. I had a lot of fun. I learned a whole lot of stuff, and I'm glad we could share all these great tips and tricks with all the rest of the FIRST community. So again, thank you guys for being here on Behind the Lines with us.
Thanks for having us.
Thank you.
Awesome.
Enjoyed it.
No, great.
Have a great
All right.
year. I'm pumped.
Oh, yes, we will.
Yeah.
Before we go, though, just a couple of quick things. We mentioned earlier, actually, Adam mentioned earlier, about a video from last year for Behind the Lines about motor selection. That video is episode 3 of Behind the Lines season 1. It's with Ken Stafford. If you go to youtube.com/FRC GameSense and then check out the playlist for Behind the Lines, it'll be right there for you to view and see on your own. And Ty, speaking of playlists, what do you have to share with us?
All right, our friends at 1114 Symbotics very recently released a SolidWorks tutorial series, and it is a very well thought out, well organized series that can get you set up and prototyping and designing in SolidWorks within a day or two. And we think that is a really great resource for teams. It shows you how to get SolidWorks for free, all the way to building an assembly and building even a drivetrain in SolidWorks. And that can really help you speed up your prototyping and design times there. So with that, we would like to thank the Symbots thank Symbotics for providing that resource for us. And we hope you had a great time watching this episode. Thanks again to our experts for putting on a great episode, and we will see you guys in 2 weeks.
Have a good night, everybody. See you later.
Have a good one.